In translational motion, we've been always dealing with these forces. F, vector. In rotational motion, we have what is called torque. Use the symbol tau, and that's the letter is a tau, and that represents torque. Now, torque is just kind of a spinny force. When you want something to accelerate or go faster angularly, like here's something going faster angularly, you have to exert a torque. Now, it gets a little bit more complicated because torque is what we call a moment. It has something to do with some value as well as a distance. And this torque, it is a vector, and it's calculated by R cross F. That is a cross product. The magnitude of it is, this is how we symbolize that. The magnitude of the torque, that's a tau, is equal to RF sine theta. And I will explain this in detail, what this R and this F and what the angle between them means. But this is a vector, and for this part, we are not going to be dealing with the vector aspect of it so much, because this torque will either be clockwise or counterclockwise for most of our problems here. But it does point in a direction indicated by the right-hand rule. For example, if something's going for you, this is counterclockwise, that's pointing towards you. Something going clockwise from your perspective, the vector points towards me. So you can use this right-hand rule, curve your fingers. If something's going around this way, that vector would point up. We don't need that vector component or that vector aspect so much right now. We will be needing it later. The next part of the analogy is when we're moving translationally, we have a resistance to translational acceleration, which we call mass, m. That is resistance to translational acceleration. In rotation, we have something called I. And I is called the angular inertia, or it's also called the moment of inertia. And again, it is a moment. A moment is something that has to do with a distance. It's got a quantity and a distance that is associated with it. And as we'll see, this moment of inertia, and I don't expect you to get this right away, it's going to be the sum of over all I of mi times ri squared. You'll see what that means momentarily. But this is the resistance to angular acceleration. So the harder this is to accelerate angularly, the more rotational or angular inertia it has, or greater moment of inertia. I should say it also called angular or rotational inertia. Rotational inertia depends on not only like what the object is and how much stuff is in it, it does depend on the axis of rotation. So when I try to spin this, and I need you to try this yourself, grab a meter stick, try to spin it like this, try to change its angular velocity like that, and then try it again like this. And you'll see one of those is much more difficult to do, because this does depend on where the little pieces, little infinitesimal pieces of mass are. The farther they are away from the axis of rotation, the greater the difficulty is to accelerate this angularly, and you will need to try that. So unlike mass, which it doesn't matter where I hold this, it's just as hard to accelerate up and down no matter where I hold it, rotating it or accelerating it rotationally does change, the difficulty does change when I hold it in different locations. So you will have to try that. Okay, we have more analogies. Let's go on to the next analogy. We also have an analogy for momentum, okay? P is momentum. That's also a vector. We have in angular motion what we call angular momentum. We use the letter L for this. Angular momentum. And if you know the equation for this, P is equal to mv, you might be able to guess the equation for this. Well, the analogy for m is I. The analogy for v is omega. So that is the angular momentum of a solid object, or really of any object. We will also find out for a particle, we have this equation. L is equal to R cross P. And we'll talk about that cross product as well. So again, you will have stuff like the fact that you can express Newton's law like this. The net force is equal to delta P over delta T. That's the net average force. In the same way, you can express the net torque as delta L over delta T. So all these analogies work perfectly. Not only is there a powerful analogy between translational and rotational motion, there's actually a relationship between the two. So this is also incredibly important to understand, but it's pretty easy to if you understand circular geometry. So for example, if you take a look at this circle right here, we have an arc length S. What is that arc length S? How far would a car travel along this circular track if it had completed a angular displacement of theta? Well, let's look at it just for, let's say it went all the way around once. What would theta be if this car or this disk had gone all the way around? Well, if there was this little dot was a car, it had gone around 2 pi. The distance it would have gone was 2 pi r. All we're doing is taking this angle theta, if it were 2 pi, in other words, a complete circle. How far is this linear distance? 2 pi times r. You just take theta and multiply it by whatever this radius is. For example, if this thing had gone halfway around, so from there to there, let's say, halfway around would be, well, what's the angle? In radians, it's pi radians times r. The arc length would be pi r. So here's how we express this. The translational distance that it travels, s, is equal to r times theta. Whatever theta is, you just multiply that by r and you get how far it's traveled in an arc. In other words, a car that has gone from here to here through an angle theta has traveled an arc length r times theta, this green distance s. Similarly, the translational speed is equal to, and the analogy and relationship continues to be parallel, you just take r and you multiply it by omega. Similarly, you could probably guess the next one, the tangential acceleration, and I'm going to just put tangential there so you can keep that in mind. It's this acceleration this way, a tangential, will equal r times, you guessed it, alpha. And the reason I have to put this tangential there is because when something's going around in a circle, it is also accelerating centripetally. So we're just talking about this linear acceleration tangentially. Often that's left out. Tangential acceleration is r alpha. Whereas the centripetal acceleration, which I'll actually introduce at this point, because centripetal acceleration AC is equal to v squared over r, we can rewrite that as, well, v is r omega, so that's r omega quantity squared over r, and that would be, when you figure that out, that just gives you r omega squared. So notice you can also figure out centripetal acceleration using your radius and your omega, your angular velocity. You can use that as well. So we have tangential acceleration, we have centripetal acceleration. This is the main relationships right here in the middle here. Those are the main ones you got to know. And you'll notice here that this is a distance, and this comes out as well. This is a distance times an angle in radians. How do the units work out? Well, this is how radians is a non-unit. If you multiply meters times radians, you get meters. Radians is a non-unit. If you multiply meters right here times radians per second, you just get meters per second. The radians just disappear. Also, meters times radians per second squared just gives you meters per second squared. So radians is a very convenient unit that can disappear whenever you want it to. It's the natural unit of angles. It is the natural unit for all of geometry. Degrees is just an arbitrary unit.